Welcome to the Nature of Light, What is a Photon presentation by Delta Group Engineering. I'll be taking you through the presentation, which you will see, is results-centric, rather than involving lengthy mathematical derivations. Of course, for those members of the audience which may be interested, full and complete derivations can be found at our website, www.deltagroupengineering.com, in PDF format. What are we going to cover? In this presentation, we'll look through a different lens, in order to answer the most fundamental of all physical questions: what is a photon? To achieve this, I'm going to take you through multiple derivations utilizing a single paradigm, that is, all matter radiates a spectrum of conjugate photon pairs, in equilibrium with a zero-point field. This presentation covers 1. The derivation of the mass and size of all existing fundamental particles and the prediction of new ones. 2. The derivation of the Hubble constant. 3. The derivation of the cosmic microwave background radiation temperature. 4. The derivation of the zero-point field energy density threshold, and 5. The cosmological evolution process. How did we calculate it from first principles? This can be achieved by 5 easy steps. Firstly, we apply dimensional analysis techniques, Buckingham's Spie theory and similarity principles to combine electricity, magnetism, and resultant electromagnetic acceleration. Secondly, we apply the equivalence principle to the pi groupings formulated. Thirdly, we apply Fourier harmonics to the equivalence principle. Next, we apply zero-point field theory to Fourier harmonics. Finally, we apply the polarizable vacuum model of gravity to the zero-point field. What errors are associated with our photon method? EGM is the name we have assigned our photon method, and is an acronym for electrogravity magnetics. This table compares our EGM prediction to physical measurement for 1. The root mean square charge radius of the proton as determined by the Selleck's collaboration. 2. The electric and magnetic radii of the proton and the magnetic radius of the neutron as reported by Hammer and Meissner. 3. The classical root mean square charge radius of the proton as defined by the National Institute of Standards and Technology. 4. The neutron mean square charge radius as reported by Kamenov, and 5. The late 2005/early 2006 top quark mass energy value as determined by the D0 collaboration. The largest error associated with any prediction, with the exception of the top quark mass energy value, is less than 0.82%. If we consider experimental uncertainty, then the EGM predictions are in fact exact. It should also be noted that the standard model of particle physics is incapable of producing comparable results for as many particles as the EGM method. Predictions such as the photon mass energy threshold by the particle data group required adjustment of the theory to fit observation. Our method for calculating this value is purely mathematical, and did not require adjustment. As can be clearly seen, the correlation is quite remarkable. I would like to draw your attention to the classical proton and Bohr radii, which are not experimental determinations, but the official values listed by the National Institute of Standards and Technology. Please also note that the error associated with the mass of the top quark is the largest compared to the earlier 2005 value listed by the particle data group. This is due to the fact that, to calculate its mass, an estimate of the root mean square charge radius is required. A minor correction of the root mean square charge radius of less than 1.5% produces the experimentally determined mass energy value precisely. Unfortunately, because the top quark is such a new particle at this stage, by comparison to others, the experimental particle physics community has not yet bedded down a world value as precisely as we would like. However, we should stress that this is a limitation of experimental physics, not the EGM method. What is the mathematical pattern responsible? The specific equation that describes the mass energy and radius relationship between all particles may be written simply. Omega sub omega denotes the harmonic cutoff frequency. St sub omega is a harmonic value representing the ratio between two spectra. The equation shown illustrates that mass energy is simply distributed, but may take many forms, depending upon the value of St sub omega. What harmonic patterns form? This table contains a list of existing and theoretical particles. There are 3 columns marked with omega sub-omega. Each column represents a different particle. From left to right, they represent the proton, electron, and up quark. The black text denotes existing particles, whilst the red text denotes theoretical particles. By inspection of the harmonics involved in the up quark column, one can see immediately that the numbers 1, 2, 3, 4, 7, 8, 9, 10, all in black text, are an obvious harmonic pattern. The red text numbers, 5 and 6, represent theoretical quark or bosons that fill in those gaps. Applying the same principles to protons and electrons, very obvious harmonic patterns form. This table emphasizes the possible existence of 3 theoretical leptons and 2 theoretical quark or bosons. However, we believe that the 2 theoretical quark or bosons are in fact intermediate vector bosons, force carriers. This table illustrates clearly that 2 fundamental particles may be represented as harmonic multiples of any arbitrarily selected fundamental particle. If the electron is utilized as the reference particle, then we may state that 2 fundamental particles may be described in terms of photons. This point shall be covered again in a preceding slide. How did we calculate cosmological properties from first principles? In simplest terms, we compress the total mass of the Milky Way galaxy and the universe down to 2 Planck energy density particles, related to each other by applying the EGM harmonic representation of fundamental particles. This produces cosmological properties, because the universe is isotropic. Hence, the mass density of any part of it, that is, our galaxy, is scalable relative to the whole universe. Thus, if our harmonic representation of fundamental matter is correct, we only need to know the mass and size of the Milky Way to determine the same properties on a cosmological scale. The primary tool employed to achieve our objectives is similitude, subject to the following simplified constraints. 1. The cosmos at an instant prior to the Big Bang is termed the primordial universe. It was characterized by a single wave function with maximum permissible energy density distributed homogeneously, analogous to a Planck scale particle such that it was dynamically, kinematically, and geometrically similar to a Schwarzschild black hole. 2. The relationship between the primordial universe and its present visible size obeys the EGM harmonic representation of fundamental particles. The Milky Way galaxy may be represented as a Planck scale particle of homogeneous energy density and equivalent total mass. This configuration has been termed the galactic reference particle, such that dynamic, kinematic, and geometric similarity exists between the primordial universe and the galactic reference particle. How did we derive the Hubble constant? The derivation of the Hubble constant may be simplified to the following process. 1. Treat all matter as radiators of gravitons. 2. Transform gravitational frequency to intensity, expressed in Janskys. 3. Derive the minimum gravitational lifetime of starving matter. 4. Relate the EGM harmonic representation of fundamental particles to the gravitational intensities of the primordial universe and the Milky Way, that is, our galactic reference particle, and 5. Solve for Hubble's constant. How did we derive the cosmic microwave background radiation temperature? The derivation of the cosmic microwave background radiation temperature may be simplified to the following process. 1. Derive an expansive scaling factor utilizing the ratio of the Hubble constant at the instant of the Big Bang, to the derived Hubble constant. 2. Derive a thermodynamic scaling factor based upon the redshifted wavelength of the Big Bang photon after Hubble time, and 3. The expansive scaling factor multiplied by the thermodynamic scaling factor yields the cosmic microwave background radiation temperature in terms of the derived Hubble constant. What numerical results did we achieve? 1. A Hubble age of 14.6 billion years. 2. A Hubble constant of 67.1 km per second per megaparsec, that is, to within 5.5% of the very rough community agreed value. 3. A cosmic microwave background radiation temperature of 2.7248 Kelvin, that is, to within 0.01% of the highly accurate physical measurement by WMAP, and 4. A galactic radius of 8.1 kiloparsec and total mass of 6.314 by 10 to the 11 solar masses, that is, to within 1.34% and 5.24% of standard community estimates respectively. What do the results demonstrate? 1. The influence of dark matter/energy upon the Hubble constant and cosmic microwave background radiation temperature is less than 1%. 2. The constitution of the universe is greater than 95% photons, less than 1% dark matter/energy and 4% atoms. 3. The average cosmological value of zero-point field energy density is -2.52 by 10 to the -13 pascals, hence, commercial energy extraction from the zero-point field, that is, the Casimir force, is unlikely because the available zero-point field energy is limited to -0.252 millijoules per cubic kilometer. What is the mathematical key? This slide emphasizes the solution pathway from harmonic representations of matter to the cosmic microwave background radiation temperature as a function of the Hubble constant. One should note that the constants shown are forwardly derived, not doctored retrospective approximations, in order to agree with physical observations, and make the solution work. This graph demonstrates the derived relationship between the Hubble constant and the cosmic microwave background radiation temperature. The equation shown is expressed in a slightly different form in relation to the preceding slide, but it's the same equation. Please just ignore any notational differences, it's purely cosmetic. Of particular and obvious importance is the shape of the curve. Although the curve has the classic blackbody radiative shape, the blackbody law was not utilized in the formulation of the curve. Another important feature of the curve is that it illustrates a cosmological temperature at an instant prior to the Big Bang of 0 Kelvin, and rose to its maximum value very rapidly. This graph demonstrates the rate of change of the cosmic microwave background radiation temperature in the time domain with key physical features represented, that is, local minima etc. This graph demonstrates the second derivative of the cosmic microwave background radiation temperature in the time domain with key physical features represented, that is, local maxima etc. This is an important graph demonstrating the rate of change of the Hubble constant in the time domain with key physical features represented, that is, local maxima etc. Next, we shall overlay some cosmological information to help us interpret this curve. With the graphical information overlaid, the distinction between cosmological inflation and expansion is very clear. One sees that the cosmological expansion period commences at the instant of maximum positive Hubble derivative. Hence, any cosmological periods prior to this specific event must be inflationary. Of particular importance, one should note that the rate of change of the Hubble constant in the time domain is presently positive, which explains the experimentally observed accelerated cosmological expansion phenomenon. The standard model of cosmology cannot explain this, but our photon method does. This graph demonstrates the second derivative of the Hubble constant in the time domain with key physical features represented, that is, local minima etc. If we graphically represent the magnitude of the first derivative of the Hubble constant in the time domain, we may dissect the cosmological inflation period as follows. In terms of the cosmological evolution process, this is the most important curve we have shown so far. In this form, it is quite apparent that the cosmological evolutionary process may be dissected into four distinct intervals termed primordial inflation, thermal inflation, Hubble inflation and Hubble expansion. Primordial inflation refers to the pre-Big Bang period when, according to the EGM method, the universe was literally an inside-out sphere. As strange as it may seem, a complete mathematical description of turning a sphere inside out without sharp creases or tearing, termed sphere eversion, is well described and understood, so, the EGM-derived characteristic of sphere eversion has solid mathematical grounding. Another way to visualize the universe prior to the Big Bang is by considering it to be analogous to a Schwarzschild black hole, but with the radius of the singularity being the outer radius of a sphere and the inner radius being the event horizon. At time t equals 0 the Hubble constant and cosmic microwave background radiation temperature had values of positive and negative infinity respectively. At the moment, when the inner and outer radii were equal, that is, the singularity radius coincided with the event horizon, the Big Bang occurred, and all physical laws became real. The temperature was 0 Kelvin and the magnitude of the Hubble constant decreased from positive infinity to h sub alpha. From the instant of the Big Bang to the instant of maximum cosmological temperature, the magnitude of the rate of change of the Hubble constant decreased to 0, as shown by the graph. After this, the rate of change of the Hubble constant in the time domain became positive, explaining the experimentally observed accelerated expansion phenomenon. All of the graphs shown were generated utilizing a deceleration parameter of 0 for two reasons. 1. Because the Wilkinson microwave anisotropy map satellite shows that the universe is almost perfectly flat, and 2. In order to calculate the Hubble age and size of the universe. However, if we reapply the EGM method based upon the derived deceleration parameter specified in the quinteressentia series, we obtain precise non-Hubble values in favorable agreement with the standard model of cosmology. In fact, we calculate a present deceleration parameter of -3.314 by 10 to the -4. It is important to emphasize that the standard model of cosmology has not produced the accelerated expansion phenomenon or negative deceleration parameter determination. The standard model of cosmology maps the cosmic microwave background radiation temperature over time in accordance with this diagrammatic representation. It is important to appreciate that the EGM method also produces these results, to a degree of precision substantially beyond the standard model of cosmology, simultaneously with the determination of the Hubble constant. Photon method summary points. 1. We have quasi-unified particle physics, by considering all particles to be photon radiators producing mass energy and radii predictions. 2. The Casimir force is also derived, based on our photon method. See quinteressentia part 3, includes new predictions, and 3. We have derived two of the most important cosmological parameters, and made new predictions. See quinteressentia part 4. So what does all this mean? 1. The gravitational spectrum is a simple, but extreme, extension of the electromagnetic spectrum. 2. There may be 5+ undiscovered particles based upon our harmonic interpretation of photons. 3. The Hubble constant and cosmic microwave background radiation temperature are related, and 4. Matter is just a condensed form of photons, hence, a photon is a propagating piece of matter. Well, I hope you've enjoyed the show. Please feel free to contact me by email or phone. The details are on the screen.